and m. And as I said before, gamma 1 to gamma n, gamma 2, etc., gamma m is equal to the neutral element of pi 1. So if we look at m1, etc., times m, then we get the identity matrix. Okay?
And this is equivalent to what?
No, this is equivalent to our equation at the moment. Now I will explain how one can reformulate the rigidity in terms of this. So we say that m1 to mm is rigid if for all n1 and m, so these are matrices in the Ln of C, such that n1, etc., nm is equal to the identity. Then, if we have for all y that ny is conjugate to mi, then m1 to mm is conjugate to n1 and m. So you have just one base change for all the same base change for all the matrices. Okay? And so now the reformulation is the following. Of course, L rigid is equivalent to m1 mn rigid. Okay, so this is basically just translation of the Riemann-Hilbert correspondence in this context. So now, what about Q-difference equations?
Just a question. It seems a little strange. I mean, you could take m1 through mn, conjugate to n1 to nm, and then just take one of the mi's and conjugate it.
Yeah.
And it'll still satisfy your first hypothesis.
Yeah, but there are the product has to be equal to the identity.
Okay.
Yeah, you're right.
Okay, thanks.
Is it known the list of such n-tuple of matters?
Sorry?
Is the list of such stable n-tuple of matters known or what?
Yeah, okay. This is a long story, but actually there is something which is called I don't remember the word. This is the work of Katz. Middle convolution. There is something which is called the middle convolution, which is due to Katz. He wrote a huge book on this subject for differential equation and for in the periodic settings for. And this point is that he has an algorithm in order to compute the rigid tuples like this using this new operation, which is the middle convolution. So, in some sense, the answer is yes. You can produce all these equations starting from rank 1 differential equation and by using two operations, namely direct sums and middle convolution.
Okay.
More or less. So what about Q-difference equations? So basically, the problem is that, of course, as I said before, we have, in the context of Q-difference equation, this picture we know what means local at zero and infinity, but we don't know what it means over C star. Okay? And so, a priori, there is not an obvious definition of what is a rigid equation for in the Q-difference case. So what I did is I started with what I explained in the hypergeometric Q-hypergeometric case, and I tried to see if this construction is suitable for this purpose. I would like to explain, but very briefly, the main point. So we start with, okay, we know that the Q-difference equations with regular singularities is equivalent to something like that. So instead of defining rigidity for Q-difference equation, we can define this in terms of this invariance. Okay, this is completely analog to what I did in the differential case.
But with a check on the P. You
For, yes, this is a good question. No, actually I simplified what I explained in the hypergeometric case, but this is actually an interesting question. What can we do when we put this over P and when we consider the logarithmic derivative? It's I don't know. It seems more complicated.
It's any infinity.
Oh yeah. Okay. So now the basic idea is okay. In the previous case, I used this matrix, the logarithmic derivative, the residue, and so on. I said maybe it's a little bit too complicated for me. I will start with something simpler, and I will just consider this matrix P. I will forget about this logarithmic derivative, and we will see later what happens. So what the basic idea is just, okay, we have A0, A infinity. Here we have P, which connects 0 to infinity. And we will consider, as in the Q hypergeometric case, that taking residue is a kind of localization. Basically this. So we consider that for all S in C star, the residue at S of P is a kind of local, local, infinitesimal, local connection at S. Okay, why not? So what we have is, from a more formal point of view, here we have a category of equations. So by E, I denote the whole category with the morphisms and so on. I don't want to define them. Here we have another category of these kind of triples with suitable morphisms. And what we did is that we have actually functors. Here I just described the effect of the functors on the objects, but you can also define the effect on the morphisms. So we have functors from this category to some local category, say CS, okay, for any S in C star. So this is global. And this is local at S. And now the obvious definition is, so let me call this functor log S, an object C of T is rigid if, okay, now for all, say D object of C, the fact that for all S in P1, we also have localization functors at 0 and infinity, but this is this is well known. Okay, so I don't explain this. It's not a problem. So for all S in P1, the fact that log S of C is isomorphic in this category to log S of D implied that C is actually isomorphic to D. So at this point we just get a definition, and we have to prove that this has some interest. The point is that one can prove that there is a numerical characterization of rigidity. This characterization is a kind of explicit formula. I can just give you an idea of what it looks like. So C is rigid, is equivalent to the fact that the sum of I from 1 to m of the dimensions of H, Y, okay. So here, Z is just the centralizer. This is a constant matrix with complex coefficient, and you just look at the centralizer, and you consider its dimension as a vector space. Okay. And here, so here I have to explain the notation. So sigma is the set of singularities of C. Rudely speaking, they are the poles of C on C star. Okay. So let me denote by S1, Sm, some representative of sigma mod QZ. Okay. There are just infinitely many. And then you consider Ry, which is the residue at Sy of C. You get a matrix with constant coefficients. And then you define H as follows. This is just the xy in Mn of C times Mn of C, such that yr is equal to r x. So this is a Lie algebra, so in particular it is a vector space, and so you can consider its dimension. And if you get this equality, then you know that your object is rigid. Actually, this is very nice because it's very similar to a characterization of rigidity due to due to cuts. So I just would like to mention that meanwhile, while I was doing this kind of things, two colleagues from Tokyo, Sakai and Yamaguchi, studied something which is quite related to this, and their work is related to the middle convolution I mentioned. And they started with something which is called the rigidity index. And this is the basic point, the starting point of their paper. And it turned out that essentially the rigidity index is the formula I get in this way. Okay, so this is very nice. You see, everything is coherent. It's perfect. And I would like to mention one more thing, which is that also it turned out that this rigidity index meaning this equation here, as a cohomological interpretation. You can see this as an Euler characteristic of some fiber bundle over the elliptic curve C times over QZ. So this is a joint work with Jacques Soulon. But okay, I should stop.
Do you have the alpha I over there or not?
The what? The alpha I?
No, H of Ri, the definition.
Ri is...
Right, that's fine.
The definition.
So in the definition, one side has an I, the other side doesn't.
There is
The,
an
the,
I.
the next one, the next line.
Okay. Here. Oh, yeah, sure.
I mean, either remove this one or add. Right.
So how hard is it to compute these objects?
Oh,
Let me remember. Actually, my first answer is not an answer because actually there is not just one notion of rigidity. There are several notions of rigidity. In my paper, I wrote down two notions, but you can produce other notions. It turns out that I studied the other notion, which is simpler than this one. So just I need to remember. But I think it's not so easy to compute this because you have some intersections of two spaces, and no, I don't know. I don't know. I know, but I think it's not so obvious.
All right. So for time consideration, because the theme of the workshop is also